This video, we're going to talk about finding points of inflection. We'll be starting with problem number 13 from the textbook. And it says f of x is equal to x cubed minus 9x squared plus 24x minus 18. A point of inflection is found by finding the second derivative and setting it equal to 0, finding those zeros of the second derivative, and those will give me the x values at which the points of inflection occur. Remember, I told you last time, don't call those numbers critical numbers because they're something different. This is the something different that they are. They are going to give us the x coordinates for the points of inflection, and the points of inflection will be points, so they will be ordered pairs. We'll have to stick those x values back into our original equation to find the points. So let's go ahead and get started here. We're going to also want to discuss the concavity of the graph, just like we did last time, but we're going to add additional information here where we are going to identify the points of inflection. So f prime of x is 3x squared minus 18x plus 24, and f double prime of x is equal to 6x minus 18. When I set this equal to 0, that gives me 6 times x minus 3 is equal to 0, x minus 3 is equal to 0, and x is equal to 3. So 3 something is a point of inflection. Let's go ahead and find that right now. So f of 3, and I'm going to use synthetic division to help me find this. I don't want to do this by hand. So remember synthetic division from pre-calculus. The coefficients here are 1, -9, 24, and -18. I'm going to bring down the 1. 3 times 1 is 3. Add that to -9 is -6. 3 times -6 is -18. Add that to 24 is 6. 3 times 6 is 18. There's my function value of 0. So I'm going to abbreviate here. My point of inflection is going to be 3, my x value here, which is on the outside. 0 is my f of x there. So there's my point of inflection for later when I identify everything. Let's go ahead and make my number line and put 3 right there in the middle, and it separates -infinity to 3 and 3 to infinity. Pick a number less than 3 and stick it into the second derivative because we're testing for concavity. So look at this factored form right here. A number less than 3, like 0, 6 times a -3 is going to give me a -18. Pick a number bigger than 3, like 4. 4 minus 3 is 1. 6 times 1 is a +6. So this is concave up here, concave down here. So we have concave down from -infinity to 3, concave up from 3 to infinity, and we have a point of inflection at 3, 0, and we need an ordered pair for that. Let's go ahead and look at number 15. Number 15 says f of x is equal to 2x cubed minus 3x squared minus 12x plus 5. I promised you last time I would talk briefly about what a point of inflection looks like on a graph. We'll get more to graphing later. But I have higher degree polynomials that have this shape where water would spill off of the graph in the part that's concave down, water would fill up on the graph. On parts that are concave up, and this place right here where the graph switches from concave down to concave up, or where it switches from concave up to concave down, which would be right about here in this graph, where it's switching from spill to fill or fill to spill. That is my point of inflection where the concavity is 0. So this portion of the graph here is concave down. This portion is concave up like a cup. You can remember that, concave down there. So this part was concave up, this part was concave down. Right? So we're interested in all those points where the concavity changes, and it'll help us to draw a better graph is what we're interested in. The big thing that we're trying to do in this chapter is to be able to draw good sketches of graphs without our graphing calculator, because we're not going to be carrying our graphing calculator around with us all the time after this class. And we're going to need to be able to do a few more things than we could just do in pre-calculus to draw good sketches, because in pre-calculus we use the calculator to find minimums and maximums. And so, I mean, that was kind of, we had to do it at that point because we didn't have any other option. But now we have calculus and the first derivative test to tell us where those minimums and maximums occur exactly, and we're not rounding them with the calculator. And we have calculus to tell us where the points of inflection are, which will help us with that. So I've found the zeros of the second derivative here for problem number 15, which was f of x is equal to 2x cubed minus 3x squared minus 12x plus 5. The first derivative was 6x squared minus 6x minus 12, and the second derivative was 12x minus 6, which was set equal to 0, and the 0 of that was 1/2. So 1/2 something is a point of inflection. Let's go ahead and do the synthetic division off to the side here. 2, -3, -12, 5. Half of 1 is, or half of 2 is 1. 1 plus -3 is -2. Half of -2 is -1. That makes a -13. Just write this as -13 halves. And this 5 is 10 halves. 10 halves plus -13 halves is -3 halves. So I have a point of inflection for later reference at 1/2, -3 halves. And we have 1/2 is my 0 of my second derivative. That cuts it into two intervals, -infinity to 1/2 and 1/2 to 0, or to infinity. So let's look for a number less than 1/2, like 0. That will make 6 times a -1 is a -6, which makes this portion concave down. A number to the right of 1/2, like 1. 2 times 1 is 2 minus 1 is 1. 6 times 1 is a +6, concave up there. So we have our summary here: concave down from -infinity to 1/2, concave up from 1/2 to infinity, and we have a point of inflection of 1/2, -3 halves. Go ahead and look at number 19 to wrap up this section. This video will have more in this section from the textbook, but let's go ahead and look at number 19 to wrap up this video on points of inflection. So f of x is equal to x times x minus 4 to the third. Now, if this were lower degrees for the exponents, if it wasn't degree 3, I probably would want to expand things to just use the basic power rule here, but I don't want to. I'm just going to go ahead and use the product rule here, with this being u times v, and u is equal to x, and v is equal to x minus 4 to the third, making u prime equal to 1, v prime is equal to 3 times x minus 4 to the second, and the derivative of the inside is 1. I won't worry about that. F prime of x is u prime v plus v prime u. And so f prime of x is equal to 1 times x minus 4 to the third plus 3x times x minus 4 to the second. When I factor that to get the x minus 4 to the second out that's common, I have x minus 4 left on the inside there plus 3x. So that's going to give me f prime of x is equal to x minus 4 to the second times 4x minus 4 is 4 times x minus 1 times x minus 4 to the second. Now, for the sake of finding the second derivative more easily, it doesn't need to be completely factored. I need two things times each other, so I'm just going to leave this there. I just factored it to make sure that x minus 4 wasn't a factor on the inside of this. It needed to combine with those other x minus 4s. It was not. It was an x minus 1. So I'm going to leave that there and call u 4x minus 4 and call v x minus 4 squared. U prime is going to be 4. V prime is going to be 2x minus 4. And when we find the second derivative here, that's u prime times v plus v prime times u. Let's do some factoring here. There's a 4 that comes out from here. 2 times 4 is 8. X minus 4, x minus 1, f double prime of x is, now we have a common factor of 4 times x minus 4. And that leaves me with an x minus 4. That leaves me with a 2 times x minus 1. Double prime of x is equal to 4 times x minus 4 times x minus 4 plus 2x minus 2. F double prime of x is equal to 4 times x minus 4 times 3x minus 6. So that 3 can come out with this 4 to make it 12. X minus 4, x minus 2. That gives me zeros of my second derivative of x minus 4 equals 0, or x minus 2 equals 0, x equals to 4, or x equals to 2. Two and 4. like that. And then we want to test something less than 2, like 0. That'll be a positive times a negative will be a positive, and this will be concave up. We want to test something between 2 and 4, like 3, be a positive times a negative will be a negative. It's concave down. And something greater than 4, like 5, will be a positive times a positive times a positive will be a positive, and this is concave up. So we have our intervals for concave up and down. Let's go ahead and look at what these critical number, what these points of inflection will be. So 2, and then my original up here. So I'm going to just have to plug it in. I can't do synthetic division because it's not written in the form to do that. So let's come back to f of x was equal to x times x minus 4 to the third. So f of 2 is 2 times 2 minus 4 to the third is 2 times negative 2 to the third is 2 times a negative 8 is a negative 16. So I have a point of inflection at 2, negative 16. And I also have f of 4 that I need to find, which is equal to 4 times 4 minus 4 cubed. Well, that's kind of easy. That's 4 times 0 cubed. 0 cubed is 0, and that's 0. So I have a point of inflection at 4, 0. So to summarize all this, we have concave up on the intervals from negative infinity to 2, union 4 to infinity, concave down from 2 to 4, and points of inflection at 2, negative 16, and 4, 0. So that'll be it for this video, and we'll come back next time and we will officially talk about using the second derivative test for extrema. I did that in a previous video, but we'll introduce that concept in the textbook now. And you'll see that where we were using the first derivative test for extrema previously, we'll use the second derivative test for extrema now. So see you for the next video.